We are here to present a final project for the course Data Center Scale Computing. Our project is to efficiently do data retrieval and processing using eBPF. So the term big data was actually coined in the year of 1987, and since then, data is becoming very huge. In fact, it's growing so rapidly that experts believe like 1 zettabyte is going to become a commonplace in the corporate technology lexicon. So processing and generating insights from these data is becoming crucial to many company and their business. So interestingly, according to one of the survey conducted by McKinsey containing B2B companies, an overwhelming 86% of respondents said that they wish they could do more with their data. So companies are interested in capturing and processing even more amount of data in the future, and they want to generate value out of it. So in the future, we need to have even more powerful and efficient data processing engines. So our goal for this project is to optimize data processing using eBPF. So for the sake of this project, we are having a very limited scope. So we are going to take one type of data processing, which is filtering, and we try to improve the performance of filtering. So for example, you have an application and you're trying to retrieve data either from a database or a Spark cluster. So there are two ways of going about it. Either you can send your filter query to the database or your Spark engine, and the database and the Spark engine can filter your data in the node or wherever the database or the Spark engine is, and it can give you the result. So this is one way of doing the filtering, or your application can get all the data and then it can do the filtering by itself. So even in both these scenario, like what we are doing is we are doing the processing in the application layer. So this is the OSI model. So what's happening is the existing data processing systems and your databases are pulling the data from the file system, and it is doing the processing in the application layer. So we thought, what if we could kind of improve this, and can we do this in a layer that is below the application layer to improve the performance? So that's what we did in this project. And now my teammate Vasant is going to take over and going to explain how it is done.
So yeah, so if you see the network layer, that's where our project is focusing right now. What are we trying to do is we're trying to extend the functionality of the application by leveraging the dynamic programmability aspect of the network layer. Shriram, next slide, please. So to achieve this, we have two major components which we used in our project. That is, one is eBPF and the other one is XDP. So eBPF or BPF is Berkeley Packet Filter. Berkeley Packet Filter was in existence since 1992, but eBPF, or the extended Berkeley Packet Filter, came into picture from the kernel versions of 3.18. What is eBPF? eBPF is an in-kernel execution engine to process virtual instruction sets. So where is BPF? So initially, BPF was designed to work only on the socket interfaces, but now with eBPF, they can be hooked onto multiple network interfaces, such as XDP, L3 or L4 layers, or even and also socket interfaces. We used XDP in our project because XDP is the earliest entry point on the networking driver, and XDP automatically triggers a BPF program on any packet reception. So apart from just XDP being a trigger for BPF, the application also can trigger BPF by using BPF system calls or having user-defined hooks. In our project, what did we do is we tried to get the filtering mechanism into the network layer by injecting BPF codes onto the XDP layer, right? So why we're doing this is because we're trying to cut down the path length where the filtering can happen at a lower layer instead of happening at a higher layer. That is the application layer, right? Coming to the project, next slide, Sriram. The architecture diagram. We hosted our whole architecture on Kubernetes, and the first component being the REST server. The client interacts with the REST server, where the REST server takes in jobs, and the job is described by 3 variables majorly. First one being the filter condition. In our project, the filter condition is starts with, right? And the second one is the source location. In our project, we have confined ourselves with the source location to be the local file system. And the third one being the target location where the data is going to sit afterwards. And that in our case would be that it would be the Redis database, right? After a server accepts the request, right, it's going to push the job into a RabbitMQ. Then comes the extractor. The extractor is going to pull the job from the RabbitMQ and wrap it around with some metadata. The extractor majorly works with the processor, and it has two major functionalities, the extractor functionalities. The first one being that it initializes the processor saying that there's a new job coming in. And after that, it pulls the data from the source location and streams it as UDP packets to the processor. Regarding the processor, Nathan would take over.
Hi, everyone. So let me explain what the processor do. It has three major functionalities. It generates eBPF programs dynamically based on the filter condition. It attaches the generated eBPF object onto the XTP interface. And third one, it filters incoming data packets and stores them in the memory buffer. It is not as easy as it sounds. Writing eBPF program is not same as writing any other high-level programs. Even though we use higher-level programming languages like C, there are certain drawbacks about it. We cannot use any of the standard libraries as they are not available at the kernel level. There is a certain way in which we are expected to write the program, else the kernel compiler will reject the code. That is, the code cannot be dynamic in nature. For example, we cannot use for loops without measuring the number of iterations. But without iterating the data packets, we cannot perform any filtering operations. In order to overcome this, we devised a framework to generate code on the fly based on the filtering condition. Once the eBPF is attached to the interface, it sends an event callback to the extractor for it to start streaming data. Once the streaming begins and data packets are filtered, we have two options. Either we can pass the data back to the application through various network layers or drop the packet as is. The main aim of the project is not to allow data packets travel all along the layers. If we do so, how can we send the data back to the application? This is when maps and common buffers come into picture. There are two namespaces, the kernel level namespace and user level namespace. The filtering operation and data filtering happens in kernel level namespace, and our application is present at the user level namespace. The application cannot access any objects directly from the kernel level namespace. Therefore, maps were introduced. It is a common memory that can be accessed from both the namespaces. We initialized a common buffer of certain size to store the filtered data that can be accessed from both the namespaces. Since the size of the buffer is fixed and we do not know the size of incoming packets, we created another service called Buffer Manager Service, which periodically polls the common buffer, fetches the data, and writes it to the target. So this is the overall architecture on how the data processing happens. Now let's move on to the demo. Here we are, and currently every container is hosted in Kubernetes. So let's quickly check if every container is working fine. So like you see that every container is working fine. So now let's go to the REST server. So this is our service, and this is the URL. Let us quickly check if there's no data present at the target currently. So I'm hitting the get API method, and yes, like you see, there is no data present. So this is a filter API through which we are going to send us the information. Currently, the filter is going to be Batman, and the source is the data.txt. So currently, this is expected that the extractor service is able to reach this particular file. So we have put this file in the local file system, and we're going to write it to the target. So currently, my job is queued in the RabbitMQ, and the corresponding services takes care of processing. Check the logs of the eBPF server. Like you see, the data processing is already complete. So let's go and check if the data has been filtered. Yes. So like you see, the data has been filtered, and it has extracted the data that starts with Batman. And let me quickly show you what is present in the data.txt file. So we have around 1000 data, and we have filtered it based on the filter